Yep, let's record it first. All right, so in my last few classes, I was teaching you VTP, VLAN trunking protocol. I told you how we can send the traffic of VLANs from one switch to another without creating the VLANs on every switch. So we have selected a switch where we created VLANs, and then we just have send them to other switches automatically. And what's the protocol we used for that? We used VLAN trunking protocol, and I hope now you have the clear understanding of VTP, right?
Yes. Yes.
So today I'm going to talk about one more protocol of switching, which is STP. STP stands for Spanning Tree Protocol, and it's same thing like I'm going to tell you. So first of all, STP stands for Spanning Tree Protocol. So the basic overview of, or you can say why we are using STP. Now, VTP we were using for VLAN trunking protocols in order to make our work easier. We used to have a centralized switch where we create VLANs and then just we advertise them to our switches within our network, whether the switches are 10, 20, 30, 40, 50, or 60. It is up to us. So we have one mode as client, another mode is server mode. But what is this STP? What is the use of it? I'm going to tell you what is it. It's a network protocol designed to prevent layer 2 loops. As I've told you, in routing, loops can occur in the same way in switching also we can have the loops. We can have the problems of loops. The packet can keep on moving in a network, all right? So in order to prevent those loops, we are using STP. Okay, like what are the techniques that we used to avoid the loops in routing? It was split horizon, right? Am I right?
Yeah.
Yep. Would you please unmute your things? That will be much better. Unmute your audio. So keep it as it is. So then I'm gonna tell. So it's a network protocol designed. It has been designed to prevent layer 2 loops. Preventing layer 3 loops, we used to have, split horizon. There was one more thing, I forgot that. But right now we have to focus on that thing I have taught you. You can go through it again, or you can have my YouTube video with you and you can go through that also. So right now we are in STP. I'm going to talk about STP only. So it's a network protocol designed to protect, or you can say prevent layer 2 loops. It's standardized, or it's standard, S-T-A-N-D, it's standardized as IEEE 802.D, 802.D protocol. So it's basically symbol is, or it's a standardized protocol of 802.D. What is it basically doing? Basically, STP blocks some ports on switches. So there is, or you can say there are two states of ports on a switch. One is in blocking state and another is in working state, all right? So that thing we have to learn how we can do that, and based on the concept of spanning tree, I'm gonna teach you how it works, and based on that, we have to make sure that one particular port should be in the blocked state so that we will prevent the loops in the layer 2, devices. So STP block some ports on switches with redundant, not with, it's with redundant links to prevent broadcast storms, BROADCAST, So basically broadcast storms are going to occur, so it's going to use some ports in the blocking state so that we can, or the switches can prevent broadcast storms and make sure that we will have the loop-free topology or network. That's the first point. So with STP in place, you can have redundant links between switches in order to provide redundancy. So redundant links means there can be more than, what do you mean by redundant? Links. Any answers?
Like if one phone was down, we will not lose connection because we have an alternative.
Yeah, so there are more than one particular cable connected to the switch, or you can say redundant links. There is one particular communication which is going on. If it's not gonna work, we will have another way to communicate with that particular switch. So that's what redundant links are going to help us. So when you will be having STP in place, you will be having redundant links between switches in order to provide redundancy, all right? So now to better understand the importance of STP and how it's going to prevent the broadcast storms on a network with redundant links, I'm going to give you a very simple example. We will have one switch. I'm going to draw one switch here. Here is another switch. We have this switch connected to this, and we have another switch here, and it's connected to this. So we have redundant links. This particular switch is connected to two links. This is connected to two, and this switch is connected to, that's S2, that's S1, and S3. So every particular switch is having two-way communication, right? 1 and 2, 1 and 2, 1 and 2 in this way. So, but every particular switch is having two redundant links, 1 and 2 for this, 1 and 2 for this, 1 and 2, correct?
Yes.
So when you talk about STP and why it's very important in a switched network, when you talk about, suppose that we take an example, suppose that let's say S1 sends a broadcast frame. When it sends a broadcast frame to S2 switch, S2, not S1 from not S3 or even S3, or you can say S1 sends a broadcast to S2 and S3 at the same time, okay? It sends a broadcast frame to S1 and S2 switch. Both switches will receive the frame and forward the frame out to every port. Are you understanding? So when both the switches will receive on this port, they will receive on this port, they will receive, and this particular switch and this particular switch they will receive, and they will forward it to all the ports. Suppose that we have only one port here, it will forward from this port, and this will also forward from the same port. And then what will happen? A loop will occur. Are you understanding? So S2 switch forwards the frame to S3 then. All right, this is S2 switch. It will forward that frame to S3, and S3 will receive that frame and forward to S1 again. Are you understanding?
Yes.
So S3 will receive that. He will think that this is another frame, and this particular S3 will receive it and forward it to S1. So S1 then again forwards this frame to S2, and that way you can say that it's a looping structure will occur. The same thing also happens in the opposite direction. Like I said to you, even S3 is going to just send a broadcast to S1 and S2. So S1 will receive the port, it will just forward it to S2. In the same way, S2 will again forward it to S3, S3 will again forward it to S1, S1 it again forward it to S2, right? This thing, what will happen? A looping structure will occur. So without STP in place, these frames would loop forever. So STP prevents loops by placing one of the switch port in blocking state. So what STP is doing, it puts the port of one of the switch in blocking states. Suppose that in this topology, you can see STP has placed one port, or you can say we will place this port in blocking state. Blocking state. Suppose that in this particular switch, this port is in the blocking state. Now what will happen? The port will no longer process any frames except the STP messages only. So if S3 receives a broadcast frame from S1, it will not send it to S2 at the time. It will not forward any particular frame to S2, and it will stop the loop at the same time. Because if S1 will send a broadcast frame to S3 and S2, maybe S2 will forward, but at the same time, S3 will not forward that. And this port will be in the blocking state. That means S2 will not be also able to receive that. Are you understanding? So this way, we can make sure that there will not be any loop in the topology, or in this type of topology where we have redundant links in place. Got it?
Yes.
Yes.
So STP is basically going to enable layer 2 redundancy. So in this example, if the link between S3 and S1 fails, STP would converge and unblock the port on S3. All right. So if the link between S3 and S1 fails, remember this thing, if the link between S3 and S1 fails, at that time automatically STP would converge and or will convert and unblock the port on S3. Then automatically it will unblock this port if the link is failed. All right, then it will automatically unblock the port and go with convergence. Clear?
Yes.
All right, so then now this is just the basic thing. Now I'm going to tell you how it works, how this STP is basically working, the main idea, the physical idea behind it. So how STP works. Okay, so let's go ahead and talk about the working of STP. First of all, let's talk about algorithms. So STP uses the algorithm. What should be the name of algorithm? Any idea? What's the name of protocol?
What?
What is the name of protocol?
Protocol? Which protocol?
This STP, yeah.
Spanning
It
tree.
stands for what?
Spanning tree.
Spanning tree protocol. Is there any algorithm with this name? In
I don't
data
know.
structures? No idea? Basically, we have the algorithm called the spanning tree algorithm. It's called as SPA. So it's going to use that. It uses the spanning tree. Have you read the data structures? Mm-hmm.
Data structures?
Yeah. No?
No.
All right, so not an issue. So it uses spanning tree algorithm, and the shortest form of it is, or short form of it is SPA. So it's going to use that to create a topology database of the network. First thing, to prevent loops, SPA places some interfaces in the forwarding state. So to prevent loops, it will place, first of all, SPA places, there are forwarding states and blocking states. So SPA places some interfaces, or you can say ports, interfaces in forwarding state, and some in some interfaces in blocking state. So these are the two states of STP. When we create a database and then it's going to put the ports or interfaces of a switch, some ports can be in forwarding state where the communication is going to be received and sent also, but some are blocked states you can set where you cannot receive anything, so they will be blocked. So how does STP decides in which state the port will be placed? That's the thing. So how does STP decides in which state the port will be placed? There are few. So I'm going to simply say there's a criteria for that. Criteria, okay? The first one is all switches in a network elect a root switch like we had in OSPF. We were talking about routing over there. So we used to have the designated router, backup designated router, and rest were just the routers. There was the name of them, I forgot that. In the same way, all switches in a local area network or in a switched network or in a layer 2 network, all switches in a network, in a network elect, an election is basically happening, they elect a root switch, okay? And
Okay.
all working interfaces, remember this thing, all switches, if there are 20, for example, there are 20 switches in a network, all those 20 switches are going to elect. They will be having an election, and election will happen and they will just elect a prime minister or the president of the country, like root, all right? So they will elect a switch and that switch will be called root switch. And how it's going to work now, how this root switch will be working, you need to remember this thing, all working interfaces on the root switch are placed in forwarding state. Remember this thing. So when a switch will be elected, a root switch, all the ports of that switch will be placed in these. This is the criteria how STP is going to decide which port will be in which particular state. And there are two states. Remember these two things, forwarding state and blocking state. Okay. So when the elections will happen, there will be a root switch. And what will happen to the root switch? All the interfaces of that switch will be placed in forwarding state. All right, so that means all the interfaces are open. All other switches, they are called as non-root switches. Non-root SW switches. All other switches are called as non-other switches. They are going to help us to determine the best path to go to the root switch. So first of all, what's the work of them? They will calculate the best path to reach to the root switch. The work of non-root switches are to determine or to calculate the best path in order to reach to the root switch. Now about the ports. The port used, remember this thing, the port used to reach the root switch That's root port. The port used to reach the root switch is placed in forwarding state. Got it? What do you understand by this example? I'm going to tell you. First of all, when you draw a topology, suppose we have 1, 2, this is connected, another switch is here, 1, 2, 3. There is one more switch, 4, 5, all right, 6, 7. These are all the switches connected and they have redundant links. Now, for example, this switch is called as root switch, okay? And they are all non N, 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 and N. Now, all the other switches have to set the best path in order to reach the root switch to give the update about the network or frames. Now, those ports which are basically helping to send the updates to determine the best path, that routes has to be placed, or those routes have to be placed to the, those ports have to be placed in the forwarding state. When you talk about this switch, so this port is connected to this switch, that's a root switch. That means this route will be, or this particular port will be in the forwarding state. And this particular switch is having this port connected to this will be placed in forwarding state. Now coming to this particular switch is having how many redundant links? 1 and 2, right? So you will see the best path. The best path switch, if this is here, so both these particular switches will be placed in forwarding state. Over here also, this switch will be placed in forwarding state, and it depends. Now, if you don't have this type of topology, then these are going to be in the forwarding state. So you just need to remember only the ports used to reach the root switch is placed in, or all the ports are placed in forwarding state. That's the second thing. Okay.
Okay.
Next, third criteria. On the shared Ethernet segments, the switch with the best path to reach, that's what I'm saying. This is the second part, which I already told you. So when you will be having shared segments, like you have one link connected to this switch and also to this switch in this way. So on the shared Ethernet segments, the switch with the best path to reach root switch is placed in forwarding state, rest or blocking state. State. The switch is called as, on the shared Ethernet segments, the switch with the best path to reach the root switch is placed on the forwarding state, and the switch is called as designated switch. The switch will be called as, designated, D-I-S-I-G-N-A-T-E-D, designated switch, and its port as the designated port. What do you understand by this thing? Any idea?
I don't know.
Yes?
Not really.
Huh? Any guesses? Just give a guess. What's it all about?
Okay, so the switch that has a port connected directly to the root switch is going to be called designated switch. and
Exactly.
all its ports called designated ports.
For example, now we have two switches here. So both are connected to the root switch. These are indirectly connected, but they are giving us the best path to reach to the root switch. All right. So they are connected. So these two are both called as designated switches, and both these ports are called as designated ports. Are you understanding? If there is only one switch, we cannot have the topology like this. We will have one topology. We will have one switch connected to other, then another, and then another. But it can be, yeah, that can be, this is the way. We cannot have this type of switches, this type of topology. So one switch will be connected to another, that another, then another, then another. All right. Or this can be the option also. But if there are this kind of situation, then both the things will be, or both the switches will be, first of all, called as designated switches, and the ports will be designated port. And then the last criteria is all other interfaces are placed in blocking state. And will not forward frames. That's it. So this is the criteria how STP is going to decide which port will be placed in which particular state. So all switches in a network that elect a root switch first. All the interfaces on the root switch will be placed in the forwarding state, and then all the non-root switches determine the best path. Those routes or those switches or non-root switches which determine the best path to reach the root switch. The port used to reach the root switch or root port is called as, or it will be placed in forwarding state. So the port used to reach to the root switch. For example, on this switch, we are using this port to reach to the, or this port also. In this way, it will just come over here. That's also, placed in the forwarding state. And after that, on the shared segments, as I've told you, Ethernet segments, the switch with the best path to reach the switch is placed in forwarding state. These are the two examples of those particular two switches. One switch will be, the switches will be called as designated switches, and the ports that we use for them are called as designated ports, and rest of the interfaces will be placed in the blocking state. So STP considers only working interfaces. Shutdown interfaces or interfaces without the cable installed or placed in a STP disabled mode. For example, you are having a switch, it's going to have 100 ports, all right? And remember this thing, you do not have to configure STP, it's by default automatically enabled. But you just need to understand the criteria how STP is going to work. Are you understanding? By default, when you purchase any switch, STP is by default going to work automatically. Then I'm going to tell you how to disable and enable it later on. But when you connect, when you will have, suppose that you have 50 ports, 60 ports, 70 ports on a switch, by default, they're all in disabled state. But when you plug in a cable, automatically that particular interface will become active. All right. So the STP considers only working interfaces. Shutdown interfaces or interfaces without the cable installed or placed in a STP or in an STP disabled state. Remember these things. So whenever you found on a network, you found some switches and then ports of them, they are not connected to cables, you should understand that by default, right now, they are in the STP disabled state. But those who are working, who are connected with cables, by default, they are having STP enabled. Are you understanding?
Yes.
Right, so let's once again talk about this topology. Now I'm going to tell you 1, 2, and these 3 switches. Redundant links are there, S1, S2, and S3. This is the topology. These are our switches. Let's say that S1 is elected as root bridge. This is root switch, not bridge. So root switch, RS. All ports on S1 will be in the forwarding state. That means this will be in the forwarding state. This will be in the forwarding state. S2 and S3, which is S2 and S3, choose ports with the lowest cost to reach to the root to be the root ports. So S2 and S3, they will choose the lowest cost to reach the root switch to be the root port. So if S2, suppose that S3 wants to this S3 switch, he wants to reach to S2, which lowest route it's gonna use? Definitely it will use this route, right?
Yes.
Yeah.
It will not use this one because it's indirectly. That means suppose the cost is 2 and here 2, that means 4. Here cost is 2, that means if it's going to go in this way, cost will be 4, that means highest cost. Here it's going to have only lowest cost, which is 2, so it will use this port, and this is going to be in the forwarding state. Are you understanding? So these
Yes.
ports are also placed in forwarding state. In the same way, S2 is using this particular port in the forwarding state, right? So on the shared Ethernet segment between S2 and S3, this is shared Ethernet segment between S2 and S3 port. For example, this is fast Ethernet 0/1 and this is fast Ethernet 0/2, or just one in both the ways. It can be one. So as W2, or you can say switch 2 has the lowest cost to reach the root switch from here. So that port is placed in the forwarding state. So to prevent the roots, suppose that switch S2, in order to reach to S3, this is the particular cost. But in order to prevent the loops, port F, this one, it can be FA, fast Ethernet 0/1, is placed in the blocking state. Like I said before, when I took the example in my first tutorial, or in just before some time, I just gave you an example of that. So in order to provide, so on the Ethernet segment between S2 and S3, port this one, it can be fast Ethernet 0/0 on switch S2, or on this way, has the lowest cost to reach the root switch. This one is having lowest cost to reach the switch. This port is placed in forwarding state. But to prevent loops, FA fastest as well, fast Ethernet 0/1 on switch S3 is placed in blocking state, because this particular port is having, if it wants to reach from here, it's gonna just have to go through this and then this, but this is having the lowest cost. It will very simply reach over here, and then this port will be called as what? Blocking state port. So blocking state port will be this. This is how it works. Got it?
Yes.
Yeah.
So a switch with the lowest switch ID will become the root switch. Remember this thing? A switch ID consists of two components. The switch's priority by default. Now how it's going to choose, or now how elections going to happen, like I said to you, router ID in OSPF. So remember this thing, note a switch with the lowest, there was highest, right? That's why I was confused in that time. So here it's switch with the lowest ID will become the root switch. Don't be confused. In OSPF, the router with highest router ID will become the designated router. All right, but here the switch with the lowest switch ID will become the root switch. A switch ID consists of two components. First is the priority, P-R-I-O-R-E-T, priority. So by default, the priority of Cisco switches is 32,768. All right. And second is MAC address of the switch. These are the two basically ways through which we can set a switch as the root switch. And there is now something called as BPDU. BPDU. What do you mean by it? Have you heard about it?
No.
BR. What's it? Any idea?
No.
Bridge Protocol Data Unit. BPDUs are basically messages used by switches to share STP information. When a switch send one message to another or share any information from one place to another, those are called as BPDUs. So BPDUs are messages used by switches to share STP information with each other in order to elect a route, like hello packets. In routers, we have hello packets, right?
Yes.
But in switches, we have BPDU. In STP, if you talk about sending the STP information, in order to elect, if you send, for example, we set the router ID over here, which is lowest one, 1.1, switch ID as 1.1.1, or priority. Sorry, we cannot set the router ID. So we have set, there are two ways, priority, and we can set the priority as maximum as 40,000. Now this is 32,000, this is 32,000. So switch S1 will be root. So these switches have to share the STP information. Even the S1 switch have to share the STP information. So the packet which other switches will receive, those packets are called as BPDUs. All right. So the most common messages are hello BPDUs. Now in routers, we used to call about hello messages, but here we have hello BPDUs. So they will